Good morning, girls. Welcome to this video lecture. I'm going to discuss the chapter Riemann integration, which is unit 2 of real analysis of your course C5 of semester 3. Good morning, girls. Today I will discuss theorem on partition, which is related with Riemann integration. Before going to the theorem, I would like to discuss few concepts related with partition, related with Riemann integration. The first one is norm of a partition. For a partition P, the length of a largest subinterval is called the norm of a partition, and this is denoted by mu P, and this value is equal to maximum of delta xi. That means if you have a partition P which has 5 subinterval and the length of subintervals are x1, x2, x3, x4 and x5, and suppose the value of x3 is highest, then mu P equal to x3. Next, refinement of P. A partition P star is called refinement of P if P star is superset of P. That means P star contains all points of P. And definitely P star has definitely P star has higher value than P. Now, if P1 and P2 are two partition, then P star is their common refinement if P star equal to P1 union P2. That means if P1 and P2 are two partition and the union of partition is equal to the next partition which is equal to P star, then P star is called refinement of P1 as well as P2. Next is lower Riemann sum defined over a partition P for a function f. This is equal to summation I equal to 1 to n mi delta I, where mi is the infimum of f in subinterval xi minus 1 xi, and delta I is the length of the subinterval in the same subinterval. And UPF is defined as summation I equal to 1 to n mi delta I, where mi, capital Mi, is the supremum of f in xi minus 1 xi. Next, the theorem is if P star is a refinement of a partition P, then for a bounded function f, first we have to prove that lower Riemann sum for a refinement P star f is greater than equal to lower Riemann sum for a partition P defined for f, and upper Riemann sum for P star is less than equal to upper Riemann sum for P. We have two partition P star and P, and we assume that P star be a refinement of P which contains just one point more than P. That means if P star is a refinement of P, then definitely P star would be a subset of P star would be a superset of P. That means the number of points in P star is larger than P. That means here we consider that P star contains only one point more than P. That means if P has 100 number of points, then P star has 101 number of points. Let that extra point be beta, and suppose that point beta is in the subinterval xi minus 1 xi. That means beta lies between xi minus 1 xi. As f is bounded over the entire interval AB, here we assume that the interval is AB because it is already mentioned that f is bounded. So it must be bounded in every subinterval of AB. Here we have assumed that m1, m2, mi be the infimum of f. The first interval is xi minus 1 beta, second is beta xi, and third is xi minus 1 xi respectively. That means m1 is infimum of this subinterval, m2 is infimum of this subinterval, and mi is infimum of this subinterval. Since these two subintervals are basically the subinterval of this interval, if mi is infimum of this interval, then mi must be less than equal to m1 and mi is less than equal to m2. Now we are going to calculate LP star f minus LPF. Our focus will be LP star F minus LPF. Now, before going to the calculation part, I would like to discuss some. We have a partition P and we have a partition star. Suppose a partition P contains points x1, x0, x1, x2 and xn, and P star contains x0, x1, x2. We have one extra point in P star which is beta, and this beta lies between xi minus 1 xi. Now from the definition of lower Riemann we have lower Riemann equal to mi delta I summation runs from I equal to 1 to n. That means we have to calculate mi for each subinterval and we have to calculate delta I for each subinterval and we have to sum that up. Now subinterval of PR, we have P here and we have P star here. Now we are going to discuss what are the subintervals of P. The subintervals of P are x0, x1, x1, x2, xi minus 1, x1 and so on. And subinterval of partition P star are x0, x1, x1, x2. Here xi minus 1 beta, beta xi. Actually this interval is divided into two subinterval here and all remain same as subinterval of P. So if we are going to calculate LPF, if we are going to calculate LPF for the partition P as well as for P star, the value of mi delta I for this interval is same for this. Actually all subintervals are same for P as well as for P star except this and this. So when we are going to calculate LP star F minus LPF, we will focus only on these three subinterval. For LPF, we will calculate the value of LPF over this subinterval, and for LP star F, we are going to calculate the value of LP star F only for first and second subinterval. Since all the subintervals of P and P star are same except xi minus 1 beta, beta xi in P star and xi minus 1 xi in P, so LP star F minus LPF focused on these subintervals only. So, and here we have LP star F minus LPF equal to m1 beta minus xi minus 1, m2 xi minus beta and minus mi xi minus 1. So here we add beta and subtract beta, and beta minus xi minus 1 is multiplied by mi minus m1 minus mi and xi minus beta, and this is a common term here we are taking out. This is xi minus beta, this is m2 minus mi. Now beta minus xi minus 1, since beta lies between xi minus 1 and xi, so this value is greater than 0, and similarly xi minus beta is also greater than 0. Now mi is less than m1 and mi is less than equal to m2, so m1 minus mi is greater than 0 and m2 minus mi is greater than 0. So all the terms in LP star F minus LPF is greater than equal to 0, so this value is greater than equal to 0. That means LP star F is greater than equal to LPF. Here's the theorem, and my lecture won't be complete without a homework. So here it is. We're going to prove the second part of the theorem. The homework is to prove U P star F is less than equal to UPF. Hope you understand this lecture, and thank you. Be safe, stay home.